Hello, welcome to my talk on using IoTDB in the COVESA Central Data Service Playground, a toolset for automotive R&D inside and outside of the vehicle. My name is Stephen Lawrence and I am a principal engineer for Renesas Electronics, an embedded semiconductor solution provider, one of the largest in the automotive domain globally. Within the COVESA Automotive Alliance, I am a board member and the Data Architecture and Infrastructure Team Lead. I would like to start by introducing COVESA and the VSS Automotive Data Model, moving on to data-centric architectures for the software-defined vehicle and how that motivated the creation of CDSP. Then finally, how we used IoTDB in CDSP, why it was chosen, how it has been integrated, some of the challenges we faced, and a look to the future. So, introduction to COVESA, the VSS data model, and automotive. COVESA is the Connected Vehicle Systems Alliance, a large open global community collaborating on addressing business and technical challenges in the connected vehicle ecosystem. Those challenges include keeping the in-vehicle digital experience up to date, embracing the customer's digital life, and integrating vehicles into broader mobility solutions. The Alliance values align with Apache and other open source groups. We are member driven and there is open collaboration on the challenges. Code is freely available on GitHub for contribution from non-members, for example. Whilst COVESA has many projects, here are some of the primary technical activities. In vehicle data, there's work on a common language for data definition and exchange, along with common interfaces for accessing data and services. In AOSP, the app framework work is there to reduce fragmentation in the automotive application market. And in the area of commercial vehicle and fleet management, there is work to leverage the common data definition for fleet management use cases. Then finally, the Alliance has a long history, 15 years or more, of hosting open source code projects. The Alliance can rightly lay claim to being one of the primary alliances for the introduction of open source into the automotive ecosystem. In the area of vehicle data, COVESA governs the vehicle signal specification. VSS is an open data model which provides an abstract view of vehicle using consistent semantics. Combine this shared description of the vehicle on board and off board and across vehicle models and manufacturers allows companies to reduce costs and innovate more quickly. As a result, it has been widely adopted by OEMs and the automotive ecosystem and is deployed in production globally. So let's look at VSS in a little bit more technical detail. VSS provides a taxonomy for properties of a vehicle which are organized in a tree structure. So the vehicle has a cabin containing doors which have properties such as whether it's locked or open. The model rules were designed to be simple so it can be used and understood across a wide range of roles from business analysts to embedded engineers. It is both human and machine readable and defined in YAML. There is tooling that allows you to export the YAML specification to other data definition formats such as JSON, GraphQL, or Protobuf. Okay, so let's discuss how the software-defined vehicle motivates us to consider new data-centric architectures for the vehicle. Let's start by discussing the scope of the logical architecture. Next-gen vehicle architectures are trending towards increasing consolidation of functions into larger ECUs. So smaller ECUs are connected to larger zone or domain controllers. which in turn are connected to large ECUs providing head unit, high performance compute, and telematic functions. We are interested in the green bounding box in the diagram, which connects these large in-vehicle ECUs to mobile devices, the cloud, and cloud to cloud. The data architecture is in part constrained by the platform on which it runs. So let's have a short discussion about that. The consolidation of functions in vehicle requires more powerful SoCs that are capable of running centralized compute and multi-domain functions with mixed criticality, from entertainment to vehicle control. Here is an example of a next-gen high-end device from Renesas called RCAR X5H. It is an SoC with 32 ARM A720 CPU cores for high compute applications, 6 R52 cores for real-time processing, and significant AI and graphics processing power. Through the use of chiplet technology, customers can create their own variant with expanded AI, NPU, and GPU power. With such platforms, we can reconsider the in-vehicle architecture, including more data processing at the edge. To achieve the software-defined vehicle, the automotive industry is seeking new viewpoints and approaches. One megatrend is data-centric architectures, where the data itself is a first-class citizen. Another is the separation of data into hierarchies, as we see below in this DIKW pyramid. At the bottom, we have the data layer, containing raw board network data in the vehicle, such as sensor data carried on the CANs, SUM-IP, or LIN buses. In the information layer, we have data that has been enriched with metadata and characterized. In the example, a value of 33 becomes an outside temperature of 33 degrees C, and a value of false becomes the window is open. In this layer lives the VSS data model I mentioned earlier, which provides an abstract model of the vehicle state and is widely adopted, along with other domain data models such as personal data. Data can be exchanged between the two layers via vehicle APIs, such as the gateway recently defined by AUTOSAR in their latest standard. In the knowledge layer, we want to put information in context. This typically means in making conditions and domain logic into a formal model, whilst also making relationships and interactions explicit. For example, triples like the Eiffel Tower is located in Paris. Together they define the rules from which you define knowledge, such as the example shown here that when temperature is above 25 degrees C, a person feels warm. Together, the domain data models in the information and knowledge layers give us controlled vocabularies for organizing knowledge. Finally, in the wisdom layer, we can act on that knowledge as in the example. This separation of concerns allows us to separate business logic from implementation and can deliver advantages in interoperability, development agility, simplicity, and costs. So in summary, data-centric architectures typically treat data as a first-class citizen. Control vocabularies such as domain data models, API specs, relationship rules, schemas, and ontologies help organize knowledge and support greater development agility. VSS is a key SDV data model that provides an abstract view of the vehicle with consistent semantics. A separation of concerns can be achieved through abstractions and data hierarchies. This is shown in the simplified diagram in the top right. The bottom layer represents the rolling chassis, which can be controlled via vehicle abstraction APIs, represented by the red line. Differentiating automotive technology is encapsulated in the middle layer. The green line represents developer APIs that provide vehicle capabilities without the need for knowledge of automotive technology. This enables a wider group of developers in the top layer to rapidly iterate new digital experiences. As shown in the diagram below, we want consistent data model and methods across in-vehicle, mobile device, and the cloud. Of course, OEMs will make different technological choices in implementation. And so in this community work, we must agree what is developed together and what is discussed at a logical level. For example, it might be decided that here you need a gateway that does X or Y, but which is left to the marketplace. Having given you a background, let's move on to the motivation for creating the playground and its use of IoTDB. The motivation for the Central Data Services Playground is to provide tools to address the challenges I described in an open, collaborative way while maintaining flexibility in system architecture and technology selection. Using open source collaboration can freely occur without the friction of proprietary licenses and NDAs. The project uses the C4 model for software architecture visualization, as it can be read by a broad range of actors and provides different levels of abstraction. Here we have the first level, the system context diagram, which shows the playground in the middle and the external systems it interacts with around it. In vehicle, the playground services would likely be running on a large ECU, such as a HPC. Looking north-south, southbound we receive native data from ECUs, simulators, real and virtual feeders and gateways, e.g. via CAN, LIN and IP buses, and in-vehicle, in VSS and other data models. Northbound, clients make data requests to implement differentiating features. These may be in-vehicle, on mobile devices, or in the cloud. Looking east-west, westbound in the cloud, big data platforms scale operations across entire vehicle fleets. Eastbound in-vehicle large ECUs such as HPC, head unit and zone controllers must cooperate and synchronize models of the vehicle state. At its core, the playground has requirements across three main areas for its building blocks. Firstly, data models. Data models such as VSS representing the vehicle, along with related data models and others representing relationships. Secondly, persistence, basically data stores. Thirdly, application logic and APIs, standardized APIs for data access and methods. Then there are additional desirable requirements such as synchronization and data processing, which provide support. Plainly, Apache IoTDB has various functions that can be used here. Finally, the toolset components should be loosely coupled and adaptable so they can be configured in multiple ways to meet the needs of different use cases. Let's translate those requirements into the current major building blocks. To implement the VSS data store, we use Apache IoTDB. In a later slide, I will describe some of the reasons it was chosen. To implement data access using VISS, we use the VISA reference implementation. VISS is a thin get, set, and subscribe REST-like API developed by the W3C and COVESA. Recently, we merged two new building blocks, the knowledge layer server, which provides AI reasoning services on the data, and the information layer server, which provides a simple data store abstraction. There are two example feeders, a bridge that allows us to stream data from the Automotive Labs virtual cloud platform, and also a socket CAN feeder. It is straightforward to integrate your own connectors through some basic glue code. Here we have a visualization of the building blocks in a C4 model container diagram. This is the second level of abstraction, showing how IoTDB is connected to other components. Within the dotted box, we have the playground core functionality. Starting in the bottom left, we have the IoTDB database. Southbound data stores write time series data into the database using its API or SQL. On the right, the Automotive bridge subscribes to defined signals in the cloud platform and then writes the stream signals into IoTDB. Database clients can then process the data. Above is the VSS data server, which receives VSS get, set, and sub requests from its clients, which it serves from the database. On the right, we have the new AI components. A knowledge engineer will define the rules which generates knowledge based on the data in the database. So let's talk in more detail about the use of IoTDB. Why IoTDB, its integration into the playground, some of the challenges we saw, and looking ahead. So why IoTDB? So obviously the OS open source license is a significant positive. Somebody can get the database at any time. They can start a project, put it down, and come back to it later without worrying about NDAs or eval licenses. I mentioned earlier that we wanted consistent methods in vehicle and the cloud. So the fact that there were edge and cloud cluster versions available of the database was considered a positive. The wide language support is also of great benefit. We have to integrate a lot of different systems, feeders, connectors. We don't get control what language they've been written in. So the fact that IoTDB has a wide language support for its native API means that typically there is language support for whatever you're trying to connect, and you can make that connection fairly simply in a kind of low code way. In some cases, no code. The wide data processing capabilities, both the built-in functions and the extended data quality library, were of great interest. You have this data in the vehicle in the cloud, and obviously you want to process it. So if you can do that within the middleware, that's very useful. For example, one common use case in automotive is data reduction, whereas typically cloud companies might want to offboard all data to the cloud for processing. That's cost prohibitive. If you can do data reduction before you transmit, you can save some significant transmission costs, especially when scaled across a whole fleet. The integration with the Apache big data stack was also a positive. If we can get the VSS data into IoTDB and IoTDB is integrated into that stack, then obviously that's a benefit because we'll gain in functionality with little to no additional work. The benchmark performance was also a positive. Synchronization and streaming was another feature that was interesting, particularly synchronization, going back to this consistent methods between in-vehicle and cloud. We see a need in vehicle for synchronization between data stores. And so built-in synchronization features are interesting. And of course, when in the cloud, cloud to cloud. The MQTT broker was an interesting feature because whilst automotive has a lot of automotive specific transport protocols, In QM code, it's interesting to have the possibility to in-vehicle use MQTT to send data. And then more recently, I mentioned that we've integrated AI in the form of rules-based deterministic semantic reasoning. But of course, there is also machine learning and LLMs. And so some of the new AI features in IoTDB, including the MCP server for LLMs, is interesting. Put together, that meant that IoTDB was an interesting solution for our problems. So I'd like to summarize the work we have done integrating IoTDB into automotive systems in the playground. The first was extending the VISA data server so it could read and write data from IoTDB. We basically extended the server so it had IoTDB as a new time series database backend. The second was the bridge that we created between the Automotive Labs virtual signal platform and IoTDB. This bridge allows you to define what signals you want to subscribe to that get streamed from the Automotive Labs platform. They're received by the bridge, and then the bridge writes them out to IoTDB. The third was integrating IoTDB into a CAN feeder. So we have a CAN feeder that supports both virtual and real CAN buses and can play back CAN dumps. It takes that CAN data along with a DBSC file that describes the data. It converts them into the VSS data model and then writes the data out to IoTDB. So basically, we extended the CAN feeder to support IoTDB as a northbound client or sync. And then finally, I briefly sort of mentioned this recent feature that we added for deterministic rule-based semantic reasoning, a new AI feature. With rule-based semantic reasoning, you have basically if then else type rules that defines a sequence of rules that when followed, you can derive knowledge. You may have a rule that defines reasoning on a piece of data along with another rule that when combined allows you to define some knowledge. Obviously, that reasoning needs to work on data. So we took streaming data that was in IoTDB from the information layer and integrated that with the knowledge layer. So the reasoner could act on the data being streamed to IoTDB. So let's talk about some of the challenges we've found in integrating IoTDB, along with some of the things we're looking forward to trying out in the future. Firstly, with some of the challenges. VSS and IoTDB tree data model both use dot notation in paths. So to avoid the IoTDB interpreting the dots in the VSS path, we backquoted them. So as in the example shown, the IoTDB path root.vin123 is separated from the VSS path vehicle.speed by the backquotes. Another thing was I mentioned that we are very interested in synchronization between data stores. We recently found that the open source IoTDB does not have the real-time sync features of the enterprise edition. So we need to investigate whether that will be appearing in the open source version or whether we can use the streaming features to do that. Another requirement in vehicle is for embedded data services, not just the cloud, but actually in the vehicle. And so we need to do more work about to what extent IoTDB and its technology can be deployed in vehicle. Obviously, the single node image could be deployed, but we also need to consider things like runtime resources and languages. Obviously, currently IoTDB is implemented in Java, which isn't necessarily a showstopper, but requires some thinking. Obviously, also TS file is another possibility there. And then looking forward, obviously IoTDB 2.0 added the new table data model. So we need to consider what features and benefits that might bring. That in part plays into the next point, which is we're very interested in schema generation tooling. So VSS has, as a data model, has hundreds of entries with potentially extended by users with a lot of metadata. And so tooling to take that schema and generate database schema is very interesting. Another area that's being considered is GraphQL SDL. So data defined using GraphQL SDL and using that to generate database schemas. I've already mentioned synchronization and streaming. So that's definitely an area that we want to investigate further, including the CADA cloud link. I also mentioned AI. And so there, we're always, as a community, looking at standardized ways to do this, the non-differentiating parts. And so we were interested in standardized time series access for machine learning, LLMs, as I mentioned, MCP server, but also for semantic reasoning. So we're very interested in talking to the community about standard ways to do that. Okay, so we're almost at an end. It's a shame that I haven't been able to be there with you in person. It would have been great to talk to you face to face and in the breaks. I'm sure we'd have had lots to discuss. As a way of ending, I just wanted to provide you some links to further information on COVESA, VSS data model, and the playground. Feel free to contact me online if there's anything you would like to discuss. So thank you for watching. I wish you well for the remainder of the summit. I hope you have a great time. Thank you. Bye.